Welcome back to the show, everyone. Today, we're diving into a fascinating research paper that explores the exciting world of large language models, or LLMs for short, and their potential to revolutionize how we optimize code. Joining us today is lead researcher Name, a lead researcher on this project, and field expert Name, a renowned expert in compiler optimization. Welcome, both of you.
Thank you for having us.
It's great to be here. So, start. Let's start with the basics. Can you give us some context on why compiler optimization is so crucial in the world of software engineering?
Sure, it's all about making software run faster and more efficiently. When we write code, it's often not in its most optimized form. Compilers come in to translate that code into machine-readable instructions, and their job is to find clever ways to improve the efficiency of those instructions. This is important because faster software leads to better performance, less energy consumption, and ultimately, a better user experience.
That makes sense. So, what are the challenges in optimizing code, especially in large scale applications?
Well, imagine you're trying to optimize a massive code base with millions of lines of code. It's like trying to find the best route through a vast maze. There are countless possibilities, and finding the ideal combination of optimizations can be incredibly complex. It's a huge challenge, especially for humans.
And this is where LLMs come in. Tell us a bit about their potential in this domain.
Absolutely. LLMs are trained on massive amounts of data, which allows them to learn complex patterns and relationships within code. They've shown great promise in generating code, translating languages, and even understanding the nuances of different programming styles. So, it's natural to think that they could also be valuable tools for optimization.
But LLMs aren't a magic bullet, right? What are some of their limitations when it comes to optimizing code?
That's a good point. Most existing LLMs for code haven't been specifically trained for compiler optimization tasks. They may be good at suggesting basic code improvements, but they can easily get confused when it comes to more complex optimizations like vectorization or parallelization. They can also make mistakes that lead to incorrect or buggy code.
That's a critical point. So, your research aims to address this gap by specifically training LLMs for compiler optimization. But how is that different from training for other code related tasks?
That's right. We introduce LLM Compiler, which is a family of foundation models specifically designed for compiler optimization. The key is that it's trained on a vast corpus of compiler intermediate representations, or IRs, and assembly code, not just high-level source code. This allows it to develop a deeper understanding of how the compiler works and how different optimizations affect the final machine code.
Interesting. Can you explain a bit more about this two-stage training process? What data is used in each stage?
In the first stage, we pre-train the model on a massive dataset of IRs and assembly code. This is crucial because it helps the model learn the fundamental language of the compiler and how different instructions are translated into machine code. Then we fine-tune the model using instruction learning. We give it examples of code, optimization passes, and the resulting optimized code, so it learns how specific compiler optimizations affect the code's structure and performance.
I see. So the LLM is not just learning to optimize, but it's learning to understand how the compiler itself optimizes. And you're not just using any code, you're using specific compiler IRs and assembly code.
Exactly. That's a key difference. Traditional code datasets focus on high-level languages like Python or C++, but we're working with the lower-level languages that the compiler uses to generate machine code. This data is crucial for the LLM to learn the intricacies of compiler optimization.
That's fascinating. But generating this kind of training data must be quite a challenge. Can you tell us more about the dataset you used and the process for creating it?
You're right, it was a complex process. We used a large dataset of publicly available code, similar to what was used to train other large language models for code. But we then processed that code to extract compiler IRs and assembly code for different architectures. This gave us a massive corpus of compiler-specific data that we used to train LLM Compiler.
And what about the instruction fine-tuning phase? You mentioned 3 tasks: compiler emulation, flag tuning, and disassembly. Can you explain each task and how they contribute to the model's learning?
Sure. In compiler emulation, we train the LLM to predict the output of the compiler. We give it unoptimized code and a list of optimization passes, and the LLM has to predict the optimized code that the compiler would produce. This helps the model learn the semantics of compiler optimizations.
That sounds like a good way to teach the LLM how the compiler thinks. And what about the flag tuning task?
Flag tuning is all about manipulating compiler settings to achieve specific optimization goals. We train the LLM to predict the best set of compiler flags to apply to a given piece of code. We use the flag settings that produce the smallest code size, but we can expand this to target other optimization goals like performance in the future.
So the LLM is essentially learning to tune the compiler for different optimization objectives. What a cool concept. And finally, you mentioned disassembly. What's that all about?
Disassembly is the inverse of compilation. We train the model to take assembly code and translate it back into compiler IR. This is useful for a number of reasons. For instance, if you want to optimize a library that's already compiled, you can use disassembly to convert it back to IR and then apply further optimizations.
Wow, that's incredibly useful. But creating training data for these tasks must be quite complex. For example, how did you get a dataset for flag tuning, where you need to find the best set of compiler flags?
You're right, it was a massive effort. We ran a large-scale random search, experimenting with thousands of different flag combinations for each program. We then selected the flags that led to the smallest code size. This process involved compiling billions of lines of code, but it was crucial for building a robust training dataset.
That's a significant investment in computational resources. And how do you ensure that the optimized code generated by the model is actually correct? I mean, compilers can be buggy too, right?
You're absolutely right. That's a big concern. To address this, we developed a tool called PassListEval. It takes a list of optimization passes generated by the LLM and evaluates it against a suite of self-testing programs. It checks if the compiler crashes or if the program's functionality breaks after applying those passes. Only the passes that pass all these tests are used in the final training data.
That's a very smart way to ensure correctness. And how about disassembly? How do you know if the LLM is translating the assembly code correctly back into IR?
For disassembly, we use a technique called round tripping. We take the IR generated by the LLM, compile it back into assembly, and then compare that assembly to the original. If they match exactly, then we know that the disassembly was successful. This provides a good lower bound on the accuracy of the model.
So, lead researcher name, you've explained this incredible training process for LLM Compiler. Now let's talk about the results. What were the key findings of your research? How does LLM Compiler perform compared to other LLMs for code optimization?
We found that LLM Compiler significantly outperforms existing LLMs in both flag tuning and disassembly tasks. In flag tuning, it achieves a significant improvement in code size compared to the standard Oz optimization level. It even surpasses the performance of advanced LLMs like GPT-4 Turbo. In disassembly, it shows a significantly higher round-trip success rate and BLEU scores than other models, indicating its ability to translate assembly code back to IR with higher accuracy.
That's impressive. As an expert in compiler optimization, what are your thoughts on these results? Do they suggest that LLMs could eventually replace traditional techniques for optimization?
I'm really excited about these findings. It shows the potential of LLMs to take on a significant role in compiler optimization. They're showing a level of understanding of compiler semantics that's simply not possible with traditional machine learning approaches. However, it's important to remember that LLMs are not ready to replace traditional techniques entirely. There are still limitations, especially when it comes to the complexity of real-world programs.
Can you elaborate on those limitations? What are the challenges that still need to be addressed?
One of the biggest challenges is the limited context window of LLMs. Current models can handle a few thousand tokens, but many real-world programs are much larger. This limits the scope of optimizations that LLMs can perform. Another challenge is the accuracy of LLM outputs. We need to develop robust techniques to ensure that the generated code is semantically correct and doesn't introduce bugs.
So there's still a lot of work to be done in refining and improving LLMs for compiler optimization. What are some potential ways to address these limitations? Could we see a future where LLMs are routinely used to optimize code for large-scale software?
Absolutely. Researchers are working on increasing the context window size of LLMs. We're also seeing advancements in techniques for verifying the correctness of LLM outputs, either through automated verification or by integrating verification into the model's training process. And finally, we need to explore alternative representations beyond text, like graphs or other data structures, to capture the complexity of code optimization in a more efficient way.
That's a fascinating glimpse into the future of compiler optimization. What are some of the future research directions that you're most excited about?
We're really interested in exploring new ways to optimize for runtime performance, not just code size. We also want to investigate how LLMs can be used for a wider range of compiler tasks, like optimizing memory allocation or parallelizing code. And finally, we're looking into new architectures for LLMs that can handle more complex code structures and larger context windows.
That's a very promising roadmap for the future. What are your thoughts on the broader impact of this research? How could LLM Compiler change the landscape of compiler optimization?
LLM Compiler has the potential to revolutionize the way we think about compiler optimization. It opens up a new world of possibilities for using LLMs to automate and improve the optimization process. This could lead to significant performance gains in software, especially in areas like machine learning and scientific computing, where performance is paramount. It's a game changer for the field.
That's a powerful statement, and it's great that you're releasing LLM Compiler under an open source license. What impact do you hope this will have on the community?
We believe that open sourcing LLM Compiler will encourage broader collaboration and accelerate research in this field. By making the model available, we hope to empower researchers and practitioners to explore, modify, and extend it according to their specific needs. We want to foster a vibrant community around LLM Compiler and drive innovation in compiler optimization.
That's a truly inspiring goal. So to summarize, LLM Compiler is a powerful new tool for compiler optimization. It's been specifically trained on compiler IRs and assembly code, which gives it a deep understanding of how compilers work. This allows it to outperform traditional techniques and even other LLMs in tasks like flag tuning and disassembly. While there are still limitations, the potential for this technology is truly remarkable. Thank you both for joining us today and sharing your insights into this groundbreaking research. This is a field we'll be watching closely in the years to come.